Hello everyone. Let us now discuss the transform methods used in digital signal processing. Signals are of two types. One is continuous time signal and the other is digital signals or discrete time signals. Continuous time signals can be of two types again, periodic and aperiodic. Similarly, the digital signals can also be of two types, periodic and aperiodic. Now there exists Fourier series representation for periodic continuous time signals, whereas the Fourier series representation does not exist for aperiodic continuous time signals. After the periodic continuous time signals are represented using the Fourier series, then we can take its Fourier transform to perform the frequency analysis of the signals. Now, in the aperiodic continuous time signals case, we will have to directly take the Fourier transform. Similar is the approach in the digital signals also. For periodic digital signals, there exists Fourier series representation, and then we can take its discrete time Fourier transform, abbreviated as DTFT. In the aperiodic digital signals case, we can take its discrete time Fourier transform because there is no Fourier series representation that exists for aperiodic digital signals, and then we can discretize the DTFT and we can obtain the discrete Fourier transform directly. From the DTFT, we will sample the DTFT and we can obtain discrete Fourier transform. We will see the details in the coming slides. Now, the study of signals and systems using sinusoidal representation is termed as Fourier analysis. The Fourier series applies to continuous time periodic signals, I have already explained. If the signal is continuous time and non-periodic, the representation is termed as the Fourier transform. Now let us start the Fourier analysis with Fourier series representation. Now any periodic signal xt, assuming that it is a finite power signal with a period of capital T seconds, can be expressed as a summation of sine waves and cosine waves. Now let's say xt is the signal which is a periodic signal, right, with finite power, and its time period is given by capital T seconds. It can be expressed in the form of summation of sine waves and cosine waves, right. This representation is known as the trigonometric Fourier series. Now here an and bn, these are the coefficients of the Fourier series. Now the fundamental frequency of xt is capital omega naught, which is equal to 2 pi by capital T radians per second or 1 by T hertz. Now we can also say f naught, which is the frequency in hertz, is equal to 1 by capital T, and omega naught in radians is equal to 2 pi f naught, right. Now, in general, the signal is also continuous with a second harmonic, because the second harmonic, third harmonic will also exist. The second harmonic will appear at T by 2 hertz, a third harmonic will appear at 3 by T hertz, and etc. and so on. The Fourier coefficients in this equation, these an and bn, so these Fourier coefficients can be calculated directly from the signal once a signal is given using the following two equations. So this is the equation for an Fourier coefficients, right. It can be calculated as 2 by t integral from minus capital T by 2 to capital T by 2 xt cos of n omega naught t dt, where n varies from 0, 1, 2 and so on. Bn is with the sine multiplication of the signal with sine wave. The integral limits are from minus capital T by 2 to capital T by 2, and the scaling factor is 2 by T. N varies from 0 onwards. Now let us take one example. Consider the square wave xt. Now this is the square wave given. The period of the square wave is 2 seconds because it starts from, this is the origin. So at 2 seconds, the cycle is completed. So therefore the period of this square wave is 2 seconds. We will have to calculate the Fourier coefficients. Now so if we try to calculate an first, then what is our xt? Xt is equal to 1 from 0 to 1, and from 1 to 2 it is -1. We will have, so we can put it in the limits. So from 0 to 1 xt is 1. So because an will cancel out and all ans will become 0, because xt minus cos of n pi t dt from limits from 0 to 1 and from 1 to 2, this is the signal. So these two will cancel out and will give us the 0 value. For this particular waveform, all the an coefficients are 0, and hence there will be no cosine wave terms in the summation equation. The b coefficients, for from 0 to 1 we will put the value of xt as 1, and from 1 to 2 we will put again the value of 1, but it will be minus sign. So minus sign will appear here, and this will be the answer for the b coefficients, 2 by n pi into 1 minus cos of n pi. Now if we look at for even values of n, the b coefficients are also 0. So because n will vary from 0 to infinity, for even values of n, the b coefficients are 0. If you try to put the even values of n here, so coefficient bn coefficients will go to 0, right? Are also 0. Now xt will be equal to a naught by 2. This is the DC value, and since cosine terms are all 0, so we will put the value of b. Cosine terms are, this ans are 0, so this term will be 0. Only sinusoidal components will be there. This sign will appear here. We will put the value of bn. Bn was calculated to be 2 over n pi 1 minus cos n pi. So this value is put from n equal to 1 to infinity, because for even values, even the b coefficients will also be 0. Now if you expand this sigma term, the first term will be 4 over pi sine pi t. Second term will be 0, which is for n equal to 2. Then it is 4 by 3 pi sine of 3 pi t, because n is 3 here. Then fourth term is the fourth harmonic will be 0, and fifth harmonic will be there. So that means we can express xt in terms of the cosine and sinusoid sine waves. Since cosine waves are the cosine term is 0, because an coefficients are 0 in this case. So only sine terms will exist in this for the representation of this signal. Now, as you keep on adding more harmonics to the summation, now to this summation in this summation value, if you keep on adding, keep on putting the values of n, you go on increasing the values of n, then this summation will get closer and closer to xt. So that means you can this representation of the representation in terms of sine and cosine waves will approach to original signal if you increase the number of harmonics in the representation. All right. Now let us look at what is Fourier transform. Although the Fourier series is a powerful concept, it suffers from one disadvantage. That is, it is only applicable to periodic signals. So it is not applicable to aperiodic signals. But most signals of practical importance are not periodic, so they are actually aperiodic. The Fourier transform pair is given by, so x capital omega is the Fourier transform of this signal, which is xt, and it is the Fourier transform can be obtained by integrating xt from minus infinity to infinity multiplied with e to the power minus j omega t dt, and the whole integral from minus infinity to infinity. And we can, from the Fourier transform, we can recover the signal back by 1 by 2 pi minus infinity to infinity x omega e to the power j omega t d omega. You see, this scaling factor is 1 by 2 pi here. In some books, you will notice that it can be 1 over under root 2 pi here and 1 over under root 2 pi here. The important thing is that the scaling factor in the calculation of x omega and the scaling factor in the calculation of xt, right? If you multiply these two scaling factors, they should be equal to 1 over 2 pi. So either out of one of the terms will contain 1 over 2 pi, or both the terms can contain 1 over under root 2 pi. So you have to be sure about that because some books will have this kind of Fourier transform pair explanation also. Now let us take an example. Evaluate the Fourier transform of a rectangular pulse shown below. The rectangular pulse is amplitude is capital A and it varies from minus tau by 2 to tau by 2 along the time axis. All right. Now we have to take its Fourier transform. The Fourier transform formula is this. So since the rectangular pulse exists from minus tau by 2 to tau by 2, so we will have the integral limits from like this minus tau by 2 to plus tau by 2 xt e to the power minus j omega t dt. Now, because it is the value between these two time values from minus tau by 2 to plus tau by 2 is a. So therefore, xt is a. So if we solve this integral, we will reach to this formula. This is basically, now if you manipulate this, this is basically sinc function sine of omega tau by 2 divided by omega tau by 2. This is a sinc function. So therefore our capital omega is equal to a tau sine of omega tau by 2 to divided by omega tau by 2, right? Now at omega equal to 0 at this point, so this will be equal to uh, if you take its limit, so that means this will be equal to 1. So you will only get the value a tau. At t approaching 0, you will get the value of x omega is a tau. At 2 pi by tau, at omega equal to 2 pi by tau, right, you will get the value as 2 pi by tau here, and along the you will at omega equal to 2 pi by tau, you will have the Fourier transform equal to 0, and similarly for minus 2 pi by tau the Fourier transform will be 0, right? The important thing is that the Fourier transform is a continuous function of frequency, and uh, magnitude of this Fourier transform represents the distribution of amplitude with frequency. So this is a uh, continuous function of frequency, right? The Fourier transform here in this case is a continuous function of frequency. Now let us take one more example where we have to find the Fourier transform of delta t function. So delta t function is 1 here at t equal to 0. So if we take its Fourier transform will be, if you calculate, will come out to be 1. So that means along complete frequency axis, there will be a constant value of the frequency spectrum, right? So that means the Fourier transform is a uh, flat response in the for the delta function. All right, and that is why delta function is used to excite the systems, because it excites the system at all values of frequency. And right, so this is also known as the response of the system, the output of the system. If you excite the system with delta input, so the response of the system is also known as the impulse response of the system, right? Now let us take one more example. Find the Fourier transform of xt equal to e to the power minus at ut. This is the Fourier transform formula. So you try to solve this integral. Integral limits will change from 0 to infinity. So e to the power minus eat, e to the power minus j omega. So if you solve it, you will get it equal to 1 over a plus j omega. Once you want to take the magnitude spectrum, so magnitude response will be 1 over a square plus omega square under root. Now let us try to calculate the inverse transform. So this is a rectangular pulse in the frequency domain. The pulse value is 1 from minus omega c to omega c, right? So we can express this Fourier transform, the frequency response, in terms of formula also, like x omega equal to 1 from omega c. Omega varies from minus omega c to here omega c also should also come, omega minus omega c to plus omega c, it is 1, and beyond uh, beyond omega c on the positive axis and on the beyond minus omega c on the negative axis, the value is 0. Now, if you try to calculate the inverse Fourier transform, so this is the inverse Fourier transform, means you are trying to recover the signal back from the Fourier transform. So the formula is this: 1 over 2 pi, limits will be minus omega c to omega c. This value will be 1. If you try to solve it so if there is a in the frequency domain, it is a rectangular pulse. Then in the time domain, you will get a sinc function as the output. Now, the sync function, the x-axis will have the time, and y-axis will have the xt signal. So at t equal to 0, the value will be equal to omega c by pi, right? At t equal to pi by omega c or minus pi by omega c, the value of xt will be 0. So this is basically the sync function. Okay. Now let us try to find the Fourier transform of xt is equal to delta t minus a. So we have to find the Fourier transform of impulse function shifted by a. The formula is integral from minus infinity to infinity delta t minus a e to the power minus j omega d dt. So this value will be 1 for t equal to a. So if we solve it, e to the power minus j omega a will be the answer. The amplitude spectrum of the impulse function, if we take the amplitude spectrum, because this is the frequency response, and if we take the modulus of this, that will become the magnitude response. The magnitude response, if you solve it, this will be equal to 1. So since Fourier transform of delta t minus a is e to the power minus j omega, its inverse Fourier transform, you will recover the impulse function back shifted by a. Right, so now let us try to find the Fourier transform of e to the power j omega 1 t. So if you use the formula, so you will be able to obtain 2 pi delta omega minus omega 1. So if you try to plot this, you will see that uh, the uh, the the output will be, the Fourier transform will be a pulse at omega 1. The height of this pulse will be 2 pi. The amplitude spectrum of e raised to the power j omega 1 t is shown below. Now let us try to find the Fourier transform of cos of omega 1 t. So cos function can be expressed using the Euler's formula, can be expressed as e to the power j omega 1 t plus e to the power minus j omega 1 t divided by 2. So we have to take its Fourier transform. So we can we can separate out the plus sign here. So half Fourier transform of the first factor and half Fourier transform of the second factor. So if you try to, we know that what is the Fourier transform of e to the power j omega 1 t. We just solved it. It is 2 pi delta omega minus omega 1. So it will be 2 will cancel out and it will be omega minus omega 1, and for this case it will be 2 pi delta omega plus omega 1. 2 will cancel out. So the Fourier transform of a cos function is two impulses. One is at omega 1 minus omega 1, the other is at omega 1. Now let us come to the discrete time Fourier transform in the discrete domain, how the Fourier transform can be obtained. Now Fourier transform of an arbitrary discrete signal, FTD means Fourier transform of a discrete signal, is also called DTFT, which is discrete time Fourier transform. Now for discrete time signals, the Fourier transform pair is defined like this: x of omega, where omega, small omega, is the digital frequency. Please remember that. X omega is equal to n going from sigma. Now integral, in place of integral, you will get sigma because this is the discrete domain. N will go from minus infinity to infinity. Xn is the input sequence, and e to the power minus j n omega, we will get the Fourier transform of a discrete sequence xn. Inverse, we can also recover back the discrete sequence from the Fourier transform with this formula. And this scaling factor, the as I already explained, either here or here, the total multiplication of the scaling factor should come to 1 over 2 pi. So if it is 1 over 2 pi here, it has to be 1. So that in some books you will see the various ways to represent the Fourier transform pair. Now where omega, small omega, is the digital frequency or relative frequency. Its fundamental period is from minus pi to pi, and omega will be, and how this digital frequency is related with the analog frequency. This is by this formula: small omega is equal to capital omega into capital T, where capital T is the sampling period. Now x omega is periodic. We already know that this x omega, which is the digital, which is the frequency response or the frequency spectrum, is periodic with period 2 pi. So that means x omega plus 2 pi will be equal to x omega. The Fourier transform of an analog signal is not periodic, right? Its Fourier transform of an analog signal will not be periodic. In the case of analog signal, if you take the Fourier transform, it will not be periodic. But in the case of digital DTFT, the Fourier transform will be periodic with a period of 2 pi. Now let's take example. If we have a delta function in discrete domain, then its Fourier transform will be equal to 1. And if we represent from minus pi to pi, it continues, of course. It is flat because the value is 1, and pi in digital domain will be equal to fs by 2. You can easily get from this relationship omega equal to capital omega t. Now let's take another example. If the discrete sequence is given by 0 for n less than 0 and a to the power n for n greater than equal to 0, mod a is less than 1. So we apply the formula. We know that how to get the frequency, how to get the Fourier transform. This is the Fourier formula for Fourier transform: x omega equal to xn e to the power multiplied by e to the power j minus j omega n. So the function, the discrete sequence is a to the power n. So we will put it here and we will change the limits from 0 to infinity. It is an e to the power minus j n omega. N can be taken out in the exponent only, and can be taken out like this, and this is equivalent to alpha to the power n, the Fourier transform of alpha to the power, and this will be equal to 1 over 1 minus a e to the power minus j omega. So you can also apply e to the power minus j omega equal to, you apply the Euler's formula, where e j theta will be equal to cos theta plus j sin theta. So you apply here. So your frequency response can be expressed as the reciprocal of 1 and 1 minus a cos omega plus j a sin omega. And if you take its magnitude response, you will have to take the mod value of the frequency response. Then this will be, of course, the square, because one term will cancel out, which will be cos square omega plus sin square omega. So that will cancel out, and you will be left with 1 over 1 under root of 1 minus 2a cos omega plus a square. And if you take the angle of I mean the phase part of this frequency response, which is a complex value, will be minus tan inverse a sin omega 1 minus cos a omega. So there you can easily calculate these things. Now if you try to calculate the magnitude response, you will see that it is the magnitude response is given by 1 over under root of 1 minus 2a cos omega plus a square. Now for omega equal to 0, cos omega is 1, so it will be 1 minus 2a plus a square. So that means it will be in the denominator, it will be under root of 1 minus a whole square. The square will cancel out with square root, and you get the value 1 over 1 minus a. So at omega equal to 0, you get this point is 1 over 1 minus a. At omega equal to pi or minus pi, this will be minus cos omega is minus 1. In that case, it will be 1 plus 2a plus whole square plus a square. So that means the factor that you will get is 1 over 1 plus a. So this value at omega equal to minus pi and pi, this value will be 1 over 1 plus a. This is the magnitude response, which is a continuous variable, right? and this is the corresponding discrete sequence, input sequence, and this is the frequency, the magnitude response of this while taking the Fourier transform. Now, as you know that here we are using the formula to take the Fourier transform. That means for any signal xn, we are multiplying for any signal xn, let's say which is a to the power n, we are multiplying it with e to the power minus j omega n, and we are getting the frequency response. But the other way to take to get the frequency response is that by using the Z transform. So if this is the sequence given, let's say xn is equal to a to the power n un, what you do is you take its Z transform. Z transform will be xz equal to 1 over 1 minus a z to the power minus 1, and replace, for getting the Fourier transform, for every z you replace it with e to the power j small omega. So here it is z to the power minus 1. So you replace this z with e to the power j omega. Ultimately, you will get e to the power minus j omega. So this is the Fourier transform basically. If you compare here, if you compare this formula and this formula, they are same. So this is another method of getting the Fourier transform or the frequency response of the signal using the Z transform. X omega written here is basically x of e to the power j omega, but for simplicity we can directly write x of omega to represent the frequency response. Now let us talk about the properties of the Fourier transform of discrete signal of DTFT. So first property is linearity, which says that if two sequences are there and they are independently multiplied by two scalars, which one scalar is first is a, that means the first sequence is multiplied by a and the second is multiplied by b, and if it is a linear, for the linearity property, the frequency responses of the two sequences individually multiplied will be also be multiplied by a, and their summation will be equal to the ax1n plus bx2n. So that is the linearity property. The other property is time shift. When there is a sequence xn delayed by k samples, that means xn minus k, if you take its Fourier transform, it will be equal to e to the power minus j omega k x omega. There is another property which is frequency shift. When xn is multiplied by e to the power j n omega naught, then the Fourier transform will be x of omega minus omega naught. Or if the Fourier transform is given, that is basically e to the power j. It can also be represented as e to the power j omega minus omega naught. If the Fourier transform is given, you can of course recover the signal back. The discrete time Fourier transform is, let us now come to the discrete Fourier transform. The discrete time Fourier transform, we have already seen that if a sequence is given, we take its DTFT, it will be equal to x of small omega, right? But this is a continuous. If you see here, this is a continuous variable. If you take the frequency response, if you take the magnitude response here, then it is a continuous variable. But if you sample this continuous output, the continuous variable, you get what we call as the discrete Fourier transform. That means if you sample the DTFT of a signal, then you get the discrete Fourier transform, right? So which is discrete waveform, and whereas the DTFT is a continuous variable. Now, DFT is a mapping of xn to another sequence. That means what will be DFT? So we are actually sampling this x omega, which is the DTFT of the discrete sequence, is given by DTFT of the discrete sequence is given by x omega. We sample this DTFT, which will be another sequence, which we call as xk, right? This is the input sequence. We take its DFT, we get xk. So DFT basically will be a mapping of the xn sequence to another sequence, which will be xk. Now the DFT denoted by xk allows to evaluate the Fourier transform x omega. So xk is we get xk after the sampling of x omega. We want to evaluate this Fourier transform x omega at various frequency points, right? This complex valued sequence xk is obtained by sampling the Fourier transform x omega at a finite number of frequency points. This sampling is conventionally performed at equally spaced points over the period extending over minus pi to pi. Now the DFT allows us to determine the frequency content of a signal, that is to perform spectral analysis. The DFT plays a central role in the implementation of a variety of digital signal processing algorithms as a result of the existence of the efficient algorithm for the fast Fourier transform. We'll come to the fast Fourier transform because FFT is an algorithm that will reduce the number of computations, and we can with a reduced amount of effort we can get the DFT values, right? With the existence of FFT algorithms, we can apply this DFT to a variety of digital signal processing algorithms. Okay, let us now try to summarize a bit what we have done till now. Is that a Fourier transform of a discrete signal, which we call as the discrete time Fourier transform, is given by x omega equal to sigma n going from minus infinity to infinity of xn, which is the discrete sequence, input discrete sequence. This will have to be multiplied by e to the power j n omega, where the fundamental period of this omega, which is the digital frequency, is from minus pi to pi. Now, this is one method of getting the Fourier transform. The other method is that other method of getting the Fourier transform of this discrete sequence xn is that we take the z transform of xn, so which will be xz. Now, for every z in the z transform, we replace z with e to the power j omega. Now, this is equivalent to evaluating the z transform on the unit circle. So once we, because in this case the magnitude of z, which is a complex variable, will be equal to 1. So that means we are putting sigma, which is the transient, which is the factor for the transient analysis. We put sigma equal to 0. That means z will be equal to e to the power j omega, meaning by this is equivalent to evaluating the z transform on the unit circle, and we get the Fourier transform from z transform. All right. Now, x omega is a continuous variable. We have already seen that. Now, if we want to analyze this continuous variable at certain frequency points, then we will sample this x omega, and in the result, when we after the sampling of x omega, what we get is the discrete Fourier transform. That means discrete Fourier transform is the sampled version of the DTFT. Right. So in that case, we get another output sequence xk, and it will be given by n going from 0 to capital N minus 1 xn e to the power minus j n 2 pi k divided by n. I will explain this in the next slide. That is, this is equivalent to sampling x omega at n, capital N, equally spaced intervals, where k varies from 0 to n minus 1. Number of time samples are n. Please remember that where n goes from 0 to capital N minus 1, these are time samples. N represents an index for time samples, whereas the n represents the time samples for the time axis, which is the x-axis, whereas k is an index which is representing the number of frequency samples. The value of frequency samples is again n. Let us see, and let me try to explain in the next slide. Now, if this is the z plane, along the x-axis is the real part of z, along the y-axis is the imaginary part of z, right? And this is for omega equal to 0. Now, if this whole 2 pi circle range is we divide this this is the continuous, the perimeter of this circle is actually a continuous representation. That means it is a continuous variable, this omega. Now, if we discretize this continuous variable and we divide the whole 2 pi circular range into equally spaced intervals, that means this interval will be given by 2 pi by capital N. That means with a factor capital N, we are dividing this whole 2 pi, right? And the first sector will be represented by k equal to, we put here k, uh, we put here a integer factor k, so it gives the various, this is the first frequency point, second frequency point, this is for k equal to 0, this is for k equal to 1, so that means it is divided by 2 pi n, this is for k equal to 2, that means it is 4 pi by n, 6 pi by n, and so on. So that means we will get the frequency points. That means this diagram is basically representing the sampling uh, of the omega values. That means n points equally spaced on unit circle. The DFT corresponds to sampling the Z transform of XZ at n points equally spaced in angle around the unit circle. All right. So that is why we get here this factor e to the power minus j n, which is 2 pi n is a division factor, and k is a multiple which explains the different frequencies. K will vary from 0 to capital N minus 1. Basically, this point will be k equal to 0, k equal to 1. Okay. Now this is the summary of what we have done till now. Is this is the input discrete sequence. This discrete sequence is we take the Fourier transform of this discrete sequence, and we get a continuous variable. That means the Fourier transform is a continuous variable. This is plotting of the magnitude response of the Fourier transform. Along x-axis is the omega. Now, that means this is also known as discrete time Fourier transform. Fourier transform of the discrete time signal. So therefore, it is also known as discrete time Fourier transform. But this is a continuous variable. If we sample the DTFT, that means we sample this continuous variable, we get the equivalent discrete Fourier transform. That means the sampled version of the DTFT. So, which will be the output of DFT will be another sequence xk, right? Where k will define the frequency points and frequency samples. All right. Now, when the DFT of a block of n samples is calculated, the assumption is that the original signal actually repeats itself periodically with period n. Clearly, for all real signals, this will not be true. Even for artificial signals, such as a pure sinusoid, this will only be true if n is a multiple of the period of the sinusoid. That means we are trying to take the DFT within certain period, which is capital N. So that means we are trying to take the DFT within a window. So this windowing process introduces a slight distortion into the frequency representation of the signal being analyzed. This is an example of the result of windowing, that this is the xn discrete sequence, right? But we are trying to take the DFT of 256 samples from from this point to this point. So that means 144 to 144 to 400. That means we are trying to, so this is our window of 256 samples. So you will see that there will be some distortion that will appear with this windowing process, with this rectangular windowing process. For example, when a 256 point DFT is taken using a rectangular window, one can see that the waveform does not repeat, and as a result, slight frequency distortion will occur when calculating xk. For example, if the sampling frequency is 8000 Hz, number of samples considered are 1000, then the frequency resolution will be 8 Hz, right? So first the f0 will be equal to 0. The first frequency will be f1 equal to 8 Hz, which is the frequency resolution. The first frequency that will appear with the after sampling the after we apply the sampling process on the DTFT will be 8 hertz, then 16 hertz, and in this way 1000 points we are considering over a range of 0 to 8000 hertz. So we can put it in this formula. That means xk will be there. So where n varies from 0 to 999, xn e to the power minus jn 2 pi k divided by 1000. K will vary also from 0 to 999. All right. So this is one example of taking the DFT. That means taking the 1000 point DFT of a discrete sequence xn. Now we can also pad the zeros and let us see what happens with the padding. So this is the discrete Fourier transform formula where k varies from 0 to n. Now to obtain more points in the DFT sequence, 0 to actually it will be n minus 1 because the n points will be there, so it has to be n minus 1. To obtain more points in the DFT sequence, we can always increase the duration of xn. Actually, the discrete sequence exists for certain points, but to increase the duration of xn, we can pad zeros into the sequence by adding additional zero valued elements. This procedure is called padding with zeros. Now, the advantage these zero valued elements contribute nothing to the sum in the above equation, but actually the advantage will be that they act to decrease the frequency spacing. That means 2 pi by n if you pad zeros into the sequence. The zero padding gives us a high density spectrum and provides a better displayed version of for plotting, but it does not give a high resolution spectrum because no new information is being added to the signal. Only we are adding zero. Okay. Now let us talk about the inverse discrete Fourier transform. The inverse DFT equation comes directly from the inverse Fourier transform equation, where xn is the discrete time sequence, and this can be obtained from the frequency samples with this formula, where small n goes from 0 to capital N minus 1, and k also goes from 0 to capital N minus 1, and there is a scaling factor of 1 by n. However, the signal which it produces from the discrete time sequence that is produced from the inverse discrete Fourier transform, the signal which the inverse Fourier transform produces will be a periodic signal repeating every capital N sample. So it will be a periodic signal which will repeat after every capital N samples. Now this is the schematic representation of DFT. X0 to x of capital N minus 1. These are the input. These are the discrete input values, and W is a twiddle factor. Its value is e to the power uh, minus j by 2 pi by n, capital N, and this k is an index here which corresponds to the frequency sample. N is a index which corresponds to the time samples, and n varies from 0 to capital N minus 1. So the input will be multiplied by the respective twiddle factors, and after that the everything is summed, which basically forms this equation. N goes from 0 to capital N minus 1. That's what is being done in the next diagram. Only the schematic representation of the equation, and we get the values of xk. This is actually the Idft equation. The representation in the block diagram is basically this equation, where xn is multiplied with this factor. Actually, we define e to the power minus j2 pi by capital N as w, and w will be raised to the power, in that case, n and k. So w is called the twiddle factor. Right. Now this is the schematic representation of the discrete Fourier transform, and this is how the DFT can be represented using a matrix formulation, what we will do is we will take the input as a vector, which is a column vector. Input goes from this xn is the input. So n varies, small n varies from 0 to capital N minus 1. So it becomes a column vector. Capital X is the corresponding to small x. It is the values in the frequency domain. That means these are the frequency samples, these are the time samples. In this case, x will be inside the bracket will be n as the index, and capital X, this is the k, inside the bracket will be k index. So these are the frequency samples and these are the time samples. And there is a matrix which will be called as the twiddle matrix, which is the DFT matrix. Basically it is an n cross n matrix, and these are the twiddle factor values. W0 in the it goes W0 in the first row, and in the first column also the same values will be there. Otherwise, in the second row, it will start from 0, 1, 2 raised to the power 0, 1, 2 up to capital N minus 1. Third row will be 0, 2, 4, and so on. In the last row, it will be 0, capital N minus 1, twice of capital N minus 1, and n minus 1, capital N minus 1 times capital N minus 1. So that's why the square is there. So therefore, we can represent the DFT as capital X corresponds to xk. That means these are the frequency sample values. That means this is also a discrete sequence. It will be equal to the multiplication of the twiddle factor matrix into the input vector, which is a column vector basically. Now, result will be the inverse DFT. Inverse DFT, in the inverse DFT, what we have to do is we have to get back the discrete sequence X back. How we can get it? This will be a scaling factor 1 over capital N. So we take the Hermitian value of the twiddle factor matrix into capital X, which are basically the frequency samples, which follows easily by checking this W Hermitian. W is equal to W and W Hermitian. This will be equal to an identity matrix where I denotes the identity matrix. Hermitian transpose is basically what is Hermitian of X? It is transpose conjugate. So this is the denotes complex conjugation. All right. Now, what are the uses of DFT? Clearly, the DFT is useful in that it allows the spectral content of a signal to be determined. Additionally, once in the frequency domain, the DFT of a signal can be processed in order to filter or alter the signal in some desired fashion. The IDFT can then be used to regenerate the processed signal. If any window other than the rectangular window has been used, then DFT and IDFT blocks must overlap by 50% if perfect reconstruction is required. So these are some uses of the DFT. And let us see how much are the computations involved in the evaluation of the DFT. By considering complex valued sequences, that means the input sequences, we find that both the DFT and its inverse DFT can be evaluated with the same algorithm. Why? Because even though the time sequence may be real valued, the DFT sequence is complex valued. The DFT sequence can also be expressed explicitly in terms of its real and imaginary parts, where let's say Hn is the discrete time sequence. It can be expressed in the real and imaginary parts. So H subscript R n plus J subscript I n. So these two are the imaginary and the real components of Hn. And Hk can also be represented in terms of the real and the imaginary components. In this case, the small n varies from 0 to capital N minus 1, and for frequency sample values, k varies from 0 to capital N minus 1. Now, Hk will be given by, of course, this formula. This is the DFT formula. Now we replace Hn with the real part and the imaginary part, and into multiplied, the whole will be multiplied by the e to the power minus jn 2 pi k divided by capital N. So we just take the we break this e to the power j some face value, meaning by e to the power j theta is cos theta plus j sin theta. So we use that formula here. So cos of 2 pi kn and sine of 2 pi kn. So this will be, and of course j factor will also. So basically, this is the real. There are two parts. One is the real part, the other is the imaginary part. So this cos, once we break this e to the power minus j, this value, then there will be four terms that will come: 1, 2, 3, and 4 terms. So these will be the four terms in which the uh, multiplication of hrn with the cos value, multiplication of hin with the sine value, hr HR value with the sine value, and this HI value with cos value. So four multiplications are there for calculating one DFT um, sample. Similarly, the case for the IDFT, if you break HK into real and imaginary parts, so there will be four multiplications, you can very well see, right? Now, if we except for the difference, now in case of DFT and IDFT, except for the difference in the signs of there will be difference in the signs of the exponents and the n 1 by n scaling factor. So if you see here, there is no minus sign, but if you see in the DFT sequence, there is a minus sign. So except for this minus sign, the calculations involved in DFT and IDFT will remain the same, right? So the same operations are performed in both transform. Both the DFT and IDFT computations require 4n real valued multiplications per point. So as I said, let's look at the DFT values. This HRN will be multiplied with cos, HIN will be multiplied with sine, this HR will be multiplied with again this sine, and HI will be multiplied with cos. So four multiplications will be there, real multiplications per point. So, but there will be n complex multiplications, and 4n square such operations are necessary to compute the n point transform, because if for one point you require 4n real valued multiplications, then for n point transform you will require 4n square uh, um, multiplications per for the computation of the DFT. Now there, so it's a huge task to go for the DFT calculations. Now we require, certainly we require some fast algorithms to implement the discrete Fourier transform, um, and we should be able to get, we should be able to solve DFT and IDFT equations with lesser number of multiplications and additions. Therefore, it is very necessary to have a faster Fourier transform calculation, a Fourier faster algorithm for calculating the Fourier transform and in inverse discrete Fourier transform. Right. So I finish my lecture here, and in the next lecture I will discuss the faster algorithms. One is the Goertzel algorithm, the other is the FFT algorithms I will discuss. Thank you. Only